Good morning, students. Today we'll talk about many random variables. Okay, so this subject is relevant if you have multiple random variables in the problem and you're interested in the expectation value of products of some of them, or if you're interested in conditional probability of some subset of random variables in the problem. And we'll discuss what is meant by conditional probability in the course of the lecture. Okay, so whatever we have learned so far in the context of a single random variable applies or extends to the discussion on multiple random variables. So let me take the set of outcome for a random variable. This time I am taking it as a vector, and it will become very clear why I have taken the random variable as a vector. So the set of outcomes, let us say, is between minus infinity to plus infinity. Okay, so that only means that I'm going to write it as my vector x between minus infinity to plus infinity. Now the meaning of this is the following: x is a random vector, which means it has components, and each component can take values between minus infinity to plus infinity. That's the interpretation of the set of outcomes for n random variables. So these are like n components of the vector random variable vector x. Okay. Now this is relevant. For example, if you take x to be the position of a gas particle in this room, then it is nothing but the x, y, z components of the position of the gas particle. Could be the position of a gas particle. Okay, you could take x as velocity. In that case, you would have three components for the velocity for the gas particles in this room. So this could be velocity. Okay, and hence suppose I am interested in finding the average momenta or average position of a particle in this room, I would be using a probability density P of x comma v. So this would be basically giving me a probability density okay for x and v of a gas particle. This simply means that if I want to know the probability of finding a gas particle in the neighborhood of some x v, which is the position and momentum of the in this room, then I simply have to compute P of x dv x comma v into d cube x into d cube v. So this will give you a probability of finding gas particles of a gas particle in the neighborhood of x plus dx y plus dx z plus dz, and the velocities. Okay, so these are like the values of positions, okay, and the velocities are within the range Vx to Vx plus dx, and the y component of velocity is in the range Vy to Vy plus dy, and the z component of velocity is in the range Vz plus dz. Okay, so this is like a 6-dimensional cube. So I'm going to draw it in 3 dimensions only, and taking so you can take x, y, and z, and here just take a point here in the space. Now this is a 3-dimensional cube at some location. The thickness of the cube is basically dx, dy, and dz. Okay, so this distance would be some roughly, d of x, and dx, dy, dz is basically the volume of this cube at location x, y, z. Yeah. Similarly, you have to take 3 axes for the momentum or velocity, and then take a volume in the velocity space, and in the 6-dimensional space of position and momentum, you will see a cube of dimension 6, which is centered at point x comma v, and the probability of finding a particle in this cube, okay, this hypercube if you want to say, is the probability that I have written here. So this is the probability that is.
That should be Vx plus dvx, right? Because
Right. So I have to make a small correction here. It's there's a typo here. This should be it is dvx, dvy, and dvz. Thanks. And so this basically is a volume element. In 6 dimensions. Okay. Now, if you want to ask a simple concept, there's a simple concept which goes as the conditional probability. We'll talk about unconditional probabilities first. Okay. So if you want to know the unconditional probability, of finding a particle in a location x. Okay, so the word unconditional probability means, suppose you want to find the probability of finding a gas particle at location x. Okay, and you don't care about velocity. You say that I don't care what the velocity is, all I want to know is what is the probability of finding a particle at location x. Now what that means is that you're asking an unconditional probability estimate. You're saying that I will take the joint probability density, one that has all the information of positions and velocity, and I'll simply integrate this over all possible velocities, because I don't care where the particle is. I don't care what is the particle's momenta or velocity. All I want to know is what is the probability of finding a particle, probability density of finding a particle in the neighborhood of. If I take this probability density and integrate over all velocities, I will get what is required, and that is the unconditional probability density of finding a particle at a location x. Okay, so this is the unconditional probability density. Okay, so now this means that my total probability or the joint probability density must be normalized. Okay, so I'm going to call this as the joint probability density, and it has dimensions of 1 upon x cube into 1 upon v cube. Okay, so it has the dimensions of 1 upon length cube into 1 upon velocity cube, some velocity scale cube. Okay, because if you integrate the total or the joint probability density over entire phase space, what you get is basically the normalization, which is 1. Okay, so here the range of the integration is your minimum velocity to maximum velocity, and the bounds of the volume of the box. Okay, so that is the meaning of the joint probability density, and knowing this, one can compute the unconditional probability density, which has been just computed in this expression. Okay. Now, so this is basically a concept that says that I want the information of a small subset of variables, and such that I don't care what are the values of the remaining subset of variables. So, like in this expression, you don't care about the velocities, because that is one subset of your variable. The other subset is positions. You say that I want to know what is the probability of finding a particle at location x. I don't care what the velocities are. So, this way you just have to integrate the joint probability density over all velocities, and this will give you the unconditional probability density on x. Similarly, you could also obtain the unconditional probability density on velocities. Okay, so another unconditional probability density that you can construct is nothing but what is the unconditional probability of finding so this is like the unconditional probability density of velocities. Again, the procedure is same. You take the joint probability density or the total probability density, which has the full information, and then you integrate out the position degrees of freedom. Okay, so you do a volume integral of this, and what you get is basically your unconditional probability of finding the velocity of a gas particle. Okay, so that's the answer to the problem. But you could also talk about conditional probability densities. Now this is more interesting. This simply means that if you want to know the probability of finding a gas particle at some location x, provided its velocity is set to some value, or you may want to know the probability density of finding a particle at a location right below the fan, for instance, provided its velocity is something. Now here you are not saying that I don't care about the remaining subset of the random variables. If you want information on x, you are also fixing the information on v, and vice versa. Okay, so this is defined as so this is like asking what is the probability density of finding a measurement on x such that the measurement on velocity is v. Okay, so this is called as the conditional probability density, and this is definitely proportional to your joint probability density, because that is my total information, and the equality can be taken by dividing this by a norm. Okay. Now, how do we determine norm? The norm can be defined by demanding that the conditional probabilities are normalized. So, you integrate on both sides with respect to positions, okay, and what you get is basically so you can write down the definition for the norm from normalizing the conditional probability density. So, I can integrate with respect to V on both sides and get the definition of N. So, this would be, since conditional probability densities are normalized, that is the requirement we are imposing, this simply becomes the integral of the joint probability density with respect to the positions. Okay, and hence I can write down the conditional probability density of finding a particle at location x such that its velocity is fixed to v. Okay, so this is the condition: finding a particle at location x such that its velocity is v. This is given as the joint probability density divided by the norm, which we have just computed as the joint probability density integrated over all space. Okay, so that's the beautiful result. And you could also write down the result for conditional probability for position for velocities. So you can also write down similarly. Okay, you can write down for the conditional probability density of velocity such that the positions are fixed to some value x. Naturally, this will come out to be the joint probability density divided by the norm, which is now simply the integration of the joint probability density over the entire volume, over the entire velocity. Okay, so these two relationships are very important, and they give us an understanding of conditional probabilities in equilibrium systems. Okay, so I'm going to note this down. Okay, and formalizing this machinery, we can only say that there is a theorem which goes by the name of Bayes theorem, and that simply is a generalization of what we have just seen. So, if you have if you want that out of the n random variables, you want information on a few of them, let us say up to m, such that the remaining random variables have taken up these values. Okay, so you are asking what is the probability of finding x1, x2, xm such that variables from m plus 1 to n have taken these values. Okay, so these are like fixed values. Okay, so this is given by a simple Bayes theorem, which says that you have the total or the joint probability density divided by simply an integration of this joint probability density over the variables Okay, this is the so-called Bayes theorem. And a simple consequence of a Bayes theorem is that if your random variables are completely uncorrelated, okay, let us take for the simple case of two variables. Okay, so if x1 and x2 are uncorrelated, then the unconditional probabilities are the same as the conditional probability. Okay, so I will first state the theorem. This applies to n random variables. I am just proving it for two variables. Okay. Now this can be very easily proved by looking at the Bayes theorem. So a Bayes theorem for just two variables would be the unconditional, the relationship between conditional probability and the unconditional probability. So if I write down the conditional probability from the previous example, then it would simply be probability of finding x1 when x2 has been fixed to some value, and this would be given as the joint probability density divided by integration of the joint probability density over all values of x1. Okay. Now since now since your variables are completely uncorrelated, I can write down the numerator as product of individual probability densities. Okay, so if the variables are uncorrelated, the joint probability density is simply product of individual probability densities. And by the same logic, I can write down the denominator as p of x1 into p of x2 integration over all values of x1. Okay, so p of x2 will come outside the bottom integral, and integration of px1 dx1 is simply 1. Because px1 is normalized. Okay, the distribution is normalized, leaving us with just pfx1. Okay, so this is the unconditional probability, and if you look at the the left hand side, what you have is basically a conditional probability. So if you look at this derivation, what you have ended up proving is that if the random variables are uncorrelated, the conditional probability density becomes the same as the unconditional probability density. Okay, so that's an important result which helps us to simplify problems, and we shall give some problems in the upcoming assignment set, and that will test your understanding of these probability concepts. Right, so now we quickly move to the next topic, which is basically the calculation of moments and cumulants in such multivariable distributions. Okay. Now, what do I mean with moments and cumulants of such distributions? Let me give you some examples. So, I'll give you an example. What is the probability of the product Vx into x? X and Vx are the x component of position and velocities of a gas particle. So, this is like a joint moment of two random variables. How do we compute this? Okay. You can compute this if you know the characteristic function of multivariable distributions. Okay. So, let us compute these moments using the definition of characteristic functions. Okay. And then we shall proceed with, and I will give you another very simple bright method, or very simple and powerful method, which is the graphical method of computing these moments. Okay. So, let us compute the characteristic function of our PDF is now multivariable PDF. Okay. Now, I could take my x1 as x, x2 as Vx, and all other values of x as 0. Then this would give me the expectation value of x Vx. This characteristic function would give me the expectation value of these variables. Now, so the characteristic function can be computed as the set of it will be a function of the set of k's that are nothing but by the definition this multidimensional Fourier transform of our multivariable distribution. Okay. And this will reduce to the integral of this exponential. Where j runs from 1 to n, p of x1, x2 all the way to xn. And this is nothing but the expectation value of the function here, which is nothing but e to the power minus I summation j going from 1 to n kj xj. Okay. And so now if you want to find out the joint moment of some x1 to the power let us say n1, x2 to the power n2 all the way to xn to the power n capital N, then this is nothing but dn1 over d of minus ik n1, these successive derivatives. So, all the way to dnn d to the power minus ik nn of my characteristic function. Okay. And this entire derivative is taken at okay at k1 equals to k2 equals to all the way up to kn equals to 0. or if you want these joint cumulants, okay, then you need the cumulant generating function, and the procedure is same. So you take these ordered derivatives of logarithm of the characteristic function, which is the cumulant generating function. Again, this is taken at the k equals to 0. Now you can see that this expression is very lengthy and appears to be very tedious. Fortunately, to compute these joint moments and cumulants, there exists a very simple diagrammatic procedure which is similar to what we have seen for single variable random distributions. So a much simpler procedure exists which is diagrammatic. Okay, procedure exists, and that is diagrammatic in nature. So for example, I take x1 equals to x, and I take n1 equals to 1, and I take x2 equals to vx, and I take n1 equals to n2 equals to 1. Okay, and I take all other powers as all other n3 all the way to nn as 0. Okay, so that means my formula here, so basically what I am trying to say is that I am computing the joint moment of x into vx. So there is a gas in this room which is at equilibrium, and what is the average value of the position multiplied by x component of the velocity. Now these are two variables. Okay, so I am going to use different symbols. I am going to use a dot and a cross. Okay, so a dot is for positions, and a cross here represents velocity, like we did for the single random variable moments. Now I can write this in two ways. I can leave them disconnected, or I can connect them. Okay, now when you leave something disconnected, then it is basically a moment. So this is nothing but moment of x into moment of vx, okay, which is also their cumulant. So we know that the first moment is also a cumulant, and when you make them connected, then this is simply a cumulant. Okay, so this is the answer to your problem. So this is nothing but cumulants of x and vx multiplied plus x into vx cumulant. Okay, so this is a very simple procedure. You can try and work it out for other combinations of other powers of x and v, and you will be surprised as to how easy this becomes. Okay, so you would be basically interested in finding out let us say x square into vx. Now how do you do it? Well, there are two x's, so I'll put two dots because the dot represents x, and there is one vx which I'll indicate as a cross, 3 points. Now I can arrange this in many ways. So one way would be to connect the two dots and leave the x as is. There is only one way you can do it. Other way is to connect the dot and the x and leave the other dot alone. Okay, now you can do it in two ways, fine, and finally you can do it, you can connect all of them, no more cases. Okay, so when you connect all of them, that closes, that's the full set of possible combinations, and let's now write them down. So two disconnected dots is nothing but x squared, okay, okay, so this is nothing but this is nothing but the square of the first moment, and I know that the moment itself is a cumulant. Writing down for cross, you just have the first cumulant of the velocity. Then we have connected dots, so we will take second cumulant of the x into moment of velocity, but then moment is also cumulant, and the third combination is 2 times and the fourth combination is, I'm going to write it here, okay. So that is the basically value for the joint moment of x square and vx. Okay, so these are the joint moments that we have computed today. Okay, so these are the joint moments. Fine. So we close this lecture here, and we'll give some problems in the tutorials along the similar lines, and we shall meet in the next lecture to discuss principle of maximum entropy, which leads to certain types of distributions such as the Gaussian distribution and the exponential distribution, profound in nature. So you must have wondered why an equilibrium distribution is Maxwell-Boltzmann like, and the reason why you get Maxwell-Boltzmann distribution always in an equilibrium system is because that's the only distribution that maximizes entropy. So if you leave a system isolated for a long time, the system will always proceed towards the direction of maximum entropy, and because Maxwell-Boltzmann distribution is a distribution of maximum entropy, you always find equilibrium isolated systems under such a distribution. So we will discuss this in the next class and do some nice problems on this. Okay. Thank you.